Digital signal processing operates with one primary objective: building mathematical systems that can selectively extract specific frequencies from a noisy signal. In the physical world, a signal is a continuous wave of energy over time, represented as x of t. Inside a computer, that physical reality becomes a discrete digital signal, an array of data points called x of n. A digital filter is an algorithm that takes this x of n array, runs calculations, and produces a smooth output array, y of n. They remove static from audio files, blur pixels in image matrices, and smooth out stock market data so analysts can spot long-term trends. In the digital realm, signal processing leaves behind the constraints of physics and electricity. It is purely an exercise in data transformation and array manipulation. To appreciate software, consider how filtering was historically performed. Analog filters rely on physical hardware components, specifically carefully arranged circuits of resistors, capacitors, and inductors. The primary flaw of physical hardware is that it exists in the real world. Analog circuits are susceptible to environmental decay, temperature fluctuations, and component aging, all of which distort how the filter behaves over time. Furthermore, once an analog filter is soldered into a circuit board and deployed, altering its behavior requires physically swapping out the components. Digital filters bypass these constraints. They are constructed entirely of software loops and basic math, specifically multiply-accumulate operations executed by a processor. Because they exist strictly as code, software filters are immune to environmental factors. An algorithm written today executes with absolute bit-for-bit mathematical precision a century from now, and can be perfectly reproduced across millions of separate devices. The shift to software allowed engineers to trade the unpredictable chemistry of physical circuits for the exact mathematical determinism of code. This chart compares analog filter architectures. The area allowing frequencies to pass unchanged is the passband. The blocked area is the stopband. Notice the green Chebyshev curve allows wavy fluctuations, known as ripple, compared to the smooth, maximally flat orange Butterworth curve. The mathematical boundary where the filter transitions to stopping a signal is the cutoff frequency, or FC. Real algorithms can't create a perfectly vertical cliff. The green Chebyshev line achieves a rapid cutoff, while the blue Bessel line manages only a slow curve. Depending on what frequencies we want to isolate, we use different configurations. A low-pass filter allows low frequencies to pass while blocking the highs, which is the logic used to send deep bass notes to a subwoofer. Conversely, a high-pass filter blocks the lows and passes the highs. Audio engineers use this to strip out the low rumbling noise of wind or heavy machinery from vocal recordings. A bandpass filter allows a narrow range through, like tuning into a specific FM radio station. A band stop or notch filter does the exact opposite, aggressively blocking a single frequency target, like deleting a 60 Hz electrical hum caused by a bad power cable. Every single one of these geometric shapes, regardless of their complexity, is generated by implementing one universal mathematical algorithm in code, the difference equation. So how does a computer actually turn a list of numbers into a precise frequency filter? It uses the difference equation. This is a formula that calculates the current output value based on a combination of past input values and past output values. The A and B variables are filter coefficients, weights defining filter behavior. The left side uses feed-forward coefficients, BK, multiplied against input X values. The right side uses feedback coefficients, AK, multiplied against past output Y values, feeding results back in. Every digital filter ever written, from a simple image blur to advanced radar tracking, is just a specific configuration of these feed-forward and feedback coefficients. Based on that equation, programmers divide digital filters into two major families. The first is the FIR, or Finite Impulse Response filter. You build an FIR filter by setting all of the feedback coefficients, the AK values, to 0. Look at this diagram outlining a low-pass filter. For a programmer, an FIR filter performs a sliding dot product called convolution. The incoming signal is sequentially multiplied against a predefined array of weights, known as the filter kernel. The primary advantage is perfect stability. Without a feedback loop, any input error simply slides out of the calculation, ensuring the system remains completely stable. FIR filters also easily maintain linear phase, All target frequencies are delayed by the exact same amount of time as they pass through the math. This prevents phase distortion, where different parts of an audio signal arrive out of sync and ruin high-fidelity sound. The main drawback is computational expense. Achieving a sharp cutoff requires a massive filter kernel, demanding millions of extra CPU cycles. A common example is a simple 3-point moving average. The code adds the current input and the 2 previous inputs, then divides by 3. Back on our diagram, look at the final output signal on the right. By averaging the adjacent points together, the rapid, high-frequency oscillations from the input signal are ironed out, leaving a clean, smooth slope. Scientists use this technique constantly to stabilize raw sensor input, smoothing out the jittery, noisy accelerometer data feeding into a smartphone step counter. Alternatively, you can configure an FIR to act as a first difference filter. By subtracting adjacent samples, it acts as a high-pass filter, stripping away smooth gradients to detect sharp edges in an image matrix. FIR filters are the highly stable workhorses of signal processing. They trade raw computational power and memory for safety, predictability, and linear phase. The alternative architecture is the IIR, or Infinite Impulse Response filter. This graph shows the underlying concept. When a single input pulse, or delta function, hits an IIR system, the feedback loop triggers an ongoing impulse response that theoretically ripples outward forever. In code, an IIR filter is a recursive loop. The calculation relies heavily on the AK coefficients we discussed earlier, meaning the exact state of the next output depends on the state of the previous output. The quintessential software implementation of an IIR system is the exponential moving average, or EMA. In this code, a programmer defines an alpha variable between 0 and 1. This alpha acts as a tuning knob, balancing the weight of the brand new incoming data against yn-1, the accumulated history of the filter's past output. The defining advantage here is supreme memory efficiency. To process thousands of data points, this recursive algorithm only needs to store exactly one previous state variable in active memory. This makes IIR filters vital for systems programming, where memory and compute cycles are highly constrained, such as estimating TCP round-trip times. The timing algorithms used in network protocols need to run instantly with almost zero overhead. However, feeding an output back into an input creates a digital feedback loop. It operates on the exact same physical principle as holding a live microphone too close to a speaker. IIR filters provide incredibly sharp cutoffs, unparalleled computational speed, and tiny memory footprints. But to get those benefits, the programmer sacrifices the absolute guarantee of algorithmic stability. That sacrifice creates the inherent danger of IIR architecture. If the feedback coefficients aren't balanced perfectly, the recursive loop triggers catastrophic algorithmic instability. You can see this danger by looking at the simplest possible IIR filter, the accumulator. It just adds the current input to the previous output. If you feed this recursive loop a constant positive input signal, even a very small one, it continually adds that number to an ever-growing total. Without a mechanism to decay the past state, the output data compounds with every iteration, growing linearly toward infinity. In software, infinity is not an option. The unstable filter rapidly generates a number too large for the computer's architecture to handle, exceeding memory limits and returning a NaN error. This fault state crashes the program instantly. Beneath the intimidating calculus and physical hardware, digital signal processing is a pure programming discipline. It translates complex frequencies into basic array iteration, dot products, and recursive state updates. Mastering the difference equation empowers software engineers to deterministically manipulate the physical world, driving advancements in everything from data science to audio engineering.